Greetings and warm welcome. I'm delighted that you've chosen to watch my talk on focus beams for use in EBSD. The content is divided into 4 chapters. First, I will briefly introduce the focus beams and surface preparation methods for EBSD and TKD. Next, I will travel through a history of development of focus beams, pinpointing the key discoveries and developments related to focus beams. It is important to note that certain aspects such as signal detection system and vacuum system, etc. will be omitted, as the intention is to provide viewers with a broad understanding rather than exhaustive account. I would like to emphasize that the content provided does not cover the entirety of the subject matter. Instead, my aim is to provide viewers with a solid foundation to begin exploring various aspects of electron microscopy in more details. Further, I will dwell on developments related to EBSD and TKD methods. And last but not least, I will summarize current and future directions related to focus beams and TKD and EBSD methods. Before we jump to the subject matter, let me share with you my passion for electron microscopy. It is now 2 decades since I started my journey with electron microscopy. It all started at the University of Science and Technology, AGH in Krakow, Poland. At the time, only analog microscopes we have available to perform scientific research. I have concluded my MSc studies with the best master thesis at the university. Next, I moved to Scotland, to the University of Aberdeen. Here I've researched the micromechanics of composite materials with pronounced microstructure. The work was done in the framework of PhD program in the group led by Professor Igor Gus. Later I moved south to the University of Manchester and worked in the group of Professor Philly Withers. Here I developed the micron-scale versions of microhole drilling and microslotting methods of residual stress measurements using focus ion beams and digital image correlation. This part of my research work is recognized with the Peterson Award from the Society of Experimental Mechanics. In the late 2014 I've started my correlative electron microscopy journey while working for FEI and the University of Manchester. I was involved in various aspects of correlative microscopy related to coordinated transfer of samples and data between micro X-ray computed tomography, plasma dual beams, later tri-beam equipped with femtosecond pulsed laser, and transmission electron microscopes. This part of my research work that is ongoing is marked with the new hardware and fine-tuned software for correlative electron microscopy. Now let me move on and present the short introduction to various aspects of focus beams. Focus beams are complex and compact systems that emit, accelerate, deflect, and raster a narrow stream of electrons, photons, here I'm referring to ultra-short laser pulses in femtosecond timescale having green and infrared wavelengths, and ions, for example noble gases, reactive gases, metal ions, also ion clusters. Here I am showing a range of signals that are coming from matter irradiated with electron beams. The most common detected signals in SEM and TM are secondary electrons, backscattered electrons, characteristic X-rays, cathodoluminescence, elastic and inelastic scattering, and transmitted electrons. In the EBSD technique, a narrow stream of electrons is directed at a point of interest on a tilted crystalline sample, typically tilted at 70 degrees. The electron beam incoherently and quasi-elastically scatters from superficial layers of the surface volume in all directions. The interaction volume can be considered as a point-like source within a crystal. The size of this incoherent scattering determines the spatial resolution of the technique and is usually measured in tens of nanometers. This scattering forms a divergent source of electrons from superficial layers of the surface volume, and some of these electrons are incident on atomic lattice planes at angles which satisfy the Bragg law. These electrons are diffracted to form a set of doublet large angle cones that corresponds to each diffracting planes, such as these schematic cones in the center image. The image produced on the EBSD detector, that is phosphor screen that convert the electron to light, or direct electron detector CMOS chip, contains characteristic Kikuchi bands which are formed where the regions of enhanced electron intensity intersect the screen, as shown both in the schematic image and the simulated EBSD patterns from rotating FCC crystal on the left. The EBSD detector records patterns that are gnomonic projections of the diffracted cones, making the bent edges appear hyperbolic. For FIBs, following signals are detected: secondary electrons, secondary ions, and sputtered ions, for example in application in SIMS, which is secondary ion mass spectroscopy. There are a number of signals coming from photon-irradiated solids: photoelectrons, fluorescence, phosphorescence, Raman scattering, etc. Laser-induced breakdown spectroscopy is a handy technique for spectral analysis of light emitted from the formed plasma plume, capable of detecting light elements such as lithium. Currently, these beams are typically used for 6 purposes: imaging, detection quantification, deposition, implantation, milling or ablation, and polishing. Here we see schematics of transmission electron microscope, scanning electron microscope, focus ion beam columns, and scanning femtosecond laser optic path. Starting from the top of columns, TM and SEM have a similar electron sources, for example tungsten filament, lanthanum or cesium hexaboride crystal source, field emission gun, thermoionic or cold field emission gun. These have different lifetime, electron energy spread, maximum electron current density, and a long-term performance stability. Focus ion beams have different types of sources depending on the ions used. The most common commercially are liquid metal ion source and plasma ion sources. I will spend more time discussing these later in the lecture. Other ion sources are gas field ionization source, liquid metal alloy ion source, low temperature ion source, magneto-optical trap ion source. Regarding ultra-short pulse lasers, the photon beam is generated with titanium sapphire or diode-pumped ytterbium-doped potassium gadolinium tungsten, that is ytterbium KGW, bulk crystal generating average output power at several watts level. Now, the electron and ion columns components below the source are quite similar, where we can find various magnetic or electrostatic lenses, apertures, blankers, and scanning coils used to shape the electron and ion beams, scan or spot dwell these on the sample. Another important parts of the focus beam columns are various detectors, for example to detect secondary electrons, backscatter electrons, and other various signals. I will talk about these signals later. Moving on to the laser system. It typically contains optical expander, iris, lenses, and scanning mirrors to raster and focus laser beam on the sample. The laser beam average power is in watts. The electron beam maximum acceleration voltage is much higher for TMs than for SEMs or FIBs. The smallest electron beam spot is achieved for TMs, well below a nanometer. FIBs have the spot size above a nanometer, while plasma FIBs have a spot size in dozen nanometer range. It is worth pointing that these are values for the smallest beam currents, typically in a picoampere range. The laser beam spot in the multi-beam instruments applications are 3 orders of magnitude larger than the plasma beams, thus having dozens of microns diameter. Practical focus beams are arranged in 6 configurations: a vertical electron beam and a side-mounted FIB or plasma FIB at an angle above 45 degrees with respect to SEM column, a vertical FIB column for liquid metal alloy ion source and side-mounted SEM column, 2 FIB columns GFI vertically and limbs on the side. Next, tri-beam system with 3 beams focused in a single spot and the beams positioned on a plane. Further, a typical 2-beam FIB-SEM system with a broad plasma beam behind the vertical SEM column. And finally, a FIB-SEM system with an external femtosecond laser unit and processing chamber. Now let me dwell on surface preparation methods for EBSD. The key material factors for 2D and 3D BSD and TKD data collection are crystalline solids, pristine surface finish, that is roughness in a few nanometer range, intact crystal structure during material removal, and no surface contamination. Now, depending on the volume of material analyzed and the required resolution of images, we can account for several material removal method suitable for EBSD or SEM imaging. These are presented on the graphs: mechanical serial sectioning, femtosecond laser serial sectioning, broad ion beam sectioning, plasma FIP and gallium FIP serial sectioning. The table below shows serial sectioning parameters for the methods and damage depth, amorphization for these methods in silicon. It is worth pointing here that the range of damage is of the same order of magnitude, where FIP and plasma FIP are the least damaging. The literature shows that when the methods are properly used, all these methods produce surface suitable for EBSD. Since the EBSD signal is formed at the few tens of nanometers superficial layer of the material. Gallium FIPs are a well-established system dedicated for work with rather small cross-sections, dozens of microns or small volumes with thin, a few nanometer thick slices. Plasma FIBs open much bigger cross-section and volumes, at the expense of slightly thicker slices. The tri-beam is a real game changer that access millimeter-sized cross-sections and large volumes, since the material removal rate is a few orders of magnitude bigger than FIP or plasma FIP. This graph summarizes the amorphization depth in silicon from a glancing action of various ion beams and a range of the acceleration voltages. These are the results of stream simulations of ion implantation ranges. The graphs also contain the voltage ranges typically used for FIBs and broad ion beams. The lower the acceleration voltage, the lower the damage is caused. In the EBSD applications, 30 kV for surface preparation gives very good results for argon, gallium and xenon ions, where xenon produces the smallest amorphization layer. In the TKD applications, we need to reduce the voltage below 5 kV for the final polishing steps, while the negligible damage is induced for voltages below 1 kV. Now, since argon and xenon are noble gases, the problem of nanoalloying and compound forming does not exist, while gallium is known for forming of low temperature eutectics and can travel millimeter far along the grain boundaries in metals, for example in aluminium. The high-resolution TM images shows gallium monolayer formed along aluminum-silicon interface. This slide summarizes a series of experiments with various laser ablation energies and its effects on the damage in the surface superficial layer in a nickel-based single crystal superalloy. The key takeaways from the slides are: each material has a characteristic parameters, namely the ablation threshold, that is the minimum fluence defined as joules per centimeter square, below which the laser is not ablating, removing material. Low fluences above and close to the ablation threshold removes material without thermal or structural effects. High fluences produce thermal and structural effects during very fast removal of material. See the king on the graph in figure A. Grain reference orientation deviation map in figure B clearly indicates the range of damage that is caused. The low fluences region experience much lower or negligible distortion of the lattice. Figure C shows a graphical representation of the spatial distribution of fluences in the high fluence region. During ablation, we are glancing the surface with the laser beam, therefore we are using the low fluence area of the beam during laser scanning. We can approach the surface and scan the laser to remove a layer. Another important aspect of surface preparation methods for EBSD is surface contamination for air-sensitive samples. This example shows a lithiated carbon anode prepared with broad ion beam and in purpose exposed to air. The surface oxidizes rapidly and a thick layer is formed, preventing any analytical probing of this cross-section. This problem can be efficiently prevented with a dedicated inner gas sample preparation and transfer system. Here I'm highlighting a various inner gas transfer system configurations based on dedicated glove box, clean connect sample transfer container, clean mill broad ion beam sample preparation system. The most advanced setup allows preparation of samples from a bulk to size-specific TM imaging and quantification. This schematic shows sample preparation, large area cross-sectioning or planar milling with the broad ion beam, and SEM imaging. The SEM, BSC, and EBSD maps shows NMC particles after clean mill cross-sectioning. Here I am showing images of elements of the Clean Connect and Clean Mill system. The glove box has a dedicated port for the Clean Connect transfer container. The transfer container is presented in a center, here attached to the SIOS dual beam. The clean mill is depicted on the right with attached transfer container. It is worth noting that the clean mill is capable of sample milling in cryogenic conditions when the dedicated DUR cryo system is attached. Now let me switch gears and start traveling through time, highlighting the significant discoveries and developments related to focus beams. Let me point here that by no means this list exhausts the subject matter. Taking a broader perspective on microscopy, it is worthwhile to delve into the 19th century and recall the scientists that paved the way for the current status of electron, ion, and light microscopy. Starting from Thomas Young and his experimental proof of dual nature of light, Michael Faraday and his work on electromagnetic induction and many other discoveries. Later James Clerk Maxwell and his work on a dynamical theory of electromagnetic field, amongst plenty of other scientific achievements. William Röntgen for the discovery of X-rays, and Joseph Thomson for discovery of electrons. Röntgen and Thomson received the Nobel Prizes in physics in the early years of 20th century. Some say that Young, Faraday and Maxwell would receive the prize as well if the one existed earlier. The beginning of 20th century brings wide spectrum of discoveries related to microscopy and associated techniques. Max von Laue, known for the discovery of the diffraction of X-rays by crystals. Father and son Henry and Lawrence Bragg are known for the law of the diffraction and first X-ray spectrometer. These scientists received Nobel Prize in Physics for their discoveries. It is worth pointing here Albert Einstein for his publications in 1917 on theoretical basis of the lasers. Also it is appropriate mentioning greatest scientists like Ernst Rutherford, Niels Bohr, Max Planck, Erwin Schrödinger and Werner Heisenberg. The wave-particle duality theory of Louis de Broglie was experimentally proven by Clinton Davison, Lester Germer in the US, and George Thomson and Alexander Reid in Britain. On the right we see the original paper published in Nature by Thomas and Reid. Again, all the scientists are Nobel Prizes recipients in physics. Hans Walter Busch, German physicist who pioneered electron optics and laid the theoretical basis for electron microscope. Now we are getting closer to the EBSD and TKD as we know today. Shoji Nishikawa and Seiichi Kikuchi discovered patterns of cathode rays from a calcite and recorded on a photographic plate, now well known as electron backscatter Kikuchi pattern. On the right we see the original paper published in Nature by Nishikawa and Kikuchi. Walter Kossel, the son of Albrecht Kossel, who won a Nobel Prize in chemistry, is known for his work in field of X-ray and description of X-ray pattern forming from diffracting crystal, similar to Kikuchi patterns, now known as Kossel cones. In the center we see first Kikuchi patterns collected and published by Hans Boersch. He likely used Ernst Ruska microscope. I will dwell on Ruska's instrument on the next slide. I suggest browsing Professor Schwarzer webpage on the history of EBSD. The link and QR code is below. The first electron microscope, a scanning microscope to be exact, was sketched in 1931 by Ernst Ruska. Here we see the original drawing. Later, in 1933, Ruska and Max Knoll in Berlin built the first functioning electron microscope with a tungsten filament electron source. Here we see a wing surface of a housefly collected with this microscope. Ernst Ruska had to wait quite a long time to be recognized for his work and receive the Nobel Prize in Physics. The first commercial electron microscope was developed in 1938 in Britain at Imperial College London. In 1938, the first regular shipped electron microscope based on Ruska's research and development work was produced by Siemens and Helsky in Berlin. In the US, at RCA Company around the same time before the Second World War, Vladimir Zvorkin was involved in development of the first American scan electron microscope. He also set the foundations in 1923 and worked on the television systems for the RCA in Camden, New Jersey. Here we see etched brass in SEM image collected by Zvorkin using the RCA electron microscope. At the same time, in Germany, Manfred von Arden also worked on television systems and electron microscopes. He developed the first scanning transmission electron microscope in around 1937. Work of Zvorkin was continued by Albert Prebus and James Hidler, who developed the first US-based scanning electron microscope. It is worth pointing that at the similar time frame, transmission electron microscopes were developed in other countries: Hitachi and Joule in Japan, Philips in the Netherlands, and Tesla in Czechoslovakia. The foundation of thin-film sample preparation for modern transmission electron microscopy and later rapid development of metallurgical and mechanics of material theories was laid around 1950. Robert Heidenreich first thinned down metal foil to electron transparency in 1949. This work was followed by Peter Hirsch and co-workers in Cambridge and Walter Bollmann in Switzerland. David Macmillan in 1951 achieved lateral resolution of 50 nanometers by using field emission gun in SEM. The first custom-built hardware for recording electron backscatter Kikuchi patterns was developed by Van Abels and Harland in 1973. For the experiments, they used Stereoscan Mk1 microscope produced by Cambridge Instruments in Britain. The graph on the left shows increases in spatial resolution of optical and electron microscopy that occurred in time, starting from light microscopy in 19th and 20th century. We see rapid improvement in resolution of both TM and SEMs in the 20th century. In the beginning of the 21st century, we observe further improvement of resolution by using more advanced methods for correction of imperfection of electron columns, higher order aberration correction, high sensitive electron detectors to work with beam sensitive samples, rapid growth of electron, cryo-electron microscopy, etc. On the right, I have listed some of publications related to development of scanning electron microscopy led by the Cambridge scientists. The link or QR code to the webpage is below if you're interested in the content. Today, the following list of top-of-the-line TMs and SEMs are commercially available from various electron microscopy technology providers. Let me move on and have a closer look at the ion beam forming technologies. First, the liquid metal ion source, or LMIS. The first publication is dated in 1914 by John Zeleny from the University of Minnesota. He published a paper on electrical discharge from liquid point. In 1961, Krohn published work on liquid metal droplets for heavy particles propulsion for application in outer space. Focus ion beam technology based on LMIS is dated back in mid-1970, where two independent groups from Argonne National Lab in the US led by Krohn and Orsi Physics in France led by Suraut were developing compact and high-brightness liquid metal ion sources. The first work on focus ion beam microscope was out in 1979, published by Zilliger and co-workers from the Hughes Research Laboratories in the US. It is worth highlighting effort of Mayer from Oxford University and Linwood Swanson from Oregon Graduate College in the 1980s. Swanson was the founder of FEI company back in the 1971. Below is a list of current FIB manufacturers that uses various ion sources. Sources such as liquid metal alloy ion source, low temperature ion source, magneto-optical trap ion source. Another method to create accelerate gas ions is gas field ionization or GFI source. Erwin Müller developed GFI in the 1950s at Penn State University, ionize and accelerate helium ions. Below we see his invention, an exemplar ion emission pattern that corresponds to the atomic arrangement at the apex of the emitter. FIB technology based on GFI is dated back in mid-1990s, developed by Micron, and in the early 2000s by FEI. Advanced lithography ion sources, a FEI spin-off company, led the microscope development until about 2005. Later, in 2006, the technology was sold to Zeiss, leading to marketing Zeiss helium ion microscope in 2008. The schematic of GFI source is in the center, while the photograph of early Micron GFIS research platform is on the right. Next, we have thermal plasma sources. The early work in this area was published in 1947 by Babat and Badarau in 1965. The inductively coupled plasma or ICP source was researched in the 1960s by Greenfield. Plasma FIB technology based on ICP source is dated back in 1980s. Micron Corporation in mid-1980s developed ICP source for ion beam deposition system for removing and deposition of materials for semiconductor applications. In the 1999, FEI company acquired Micron and continues development of ICP sources for FEI electron microscopy, now Thermo Scientific portfolio. Another type of ion plasma source is based on the electron cyclotron resonance or ECR. Richard Geller at CEA France developed ECR in the 1960s. Louis-Jacques Celona further improved ECR in the 70s at ECA and in the 1980s at Oak Ridge National Laboratory in the US. Plasma FIB technology based on ECR source is dated back in 1990s. Emmons, Schenkel and Wickersham developed ECR in the 1990s at Berkeley Lab, US and CMAP, France to analyze and accelerate xenon and argon. Since 1998, Orsi Physics is leading the development of plasma sources based on the ECR technology. On this slide, I'm presenting single-focus ion beam scanning microscopes. FEI launched first gallium liquid metal ion source FIB in 1989. Later, Micron presented FIB, both dedicated rather for semiconductor applications. First academic FIB based on XL30 SEM platform was delivered to Cambridge University in 1995. NIST in the US installed Zeiss Orion workstation in 2008, while FEI Vion single-column workstation was delivered in 2011. Now let me focus on dual beam systems. This year, 2023, proudly marks 30 years of dual beam innovations. Starting from dual beam 620 presented in 1993, we have a long list of FIB-SEMS platforms for various applications. Year 2012 marks first experimental tri-beam based on a Strata 235 gallium FIB-SEM and femtosecond laser. The system developed in collaboration with the University of California, Santa Barbara. In 2014, plasma FIB-SEM based on Helios platform was presented publicly. From 2019, Hydra Helios multi-primary ion dual beams is available. In the next year, 2020, the first commercial tri-beam based on Helios xenon plasma dual beam was presented. In 2021, the tri-beam was extended with multi-primary ion capabilities, known as Laser Hydra Helios dual beam. Today, the following list of top-of-the-line FIPSEM are commercially available from various electron microscopy technology providers. These platforms have different ion sources: liquid metal ion source, liquid metal alloy ion source, ICP, and ECR. Albert Einstein, while probably working at ETH Zurich at the time, laid theoretical basis of the lasers. His work was published in 1917. Einstein received the Nobel Prize in Physics in 1921 for his service to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Charles Townes, while working at the Columbia University, presented in 1951 the first practical maser, that is abbreviation for microwave amplification by stimulated emission of radiation. For his invention, he received Nobel Prize in Physics in 1964, along with Nikolai Basov and Alexander Prokhof. Theodor Maiman, while working at the Hughes Research Laboratories, developed in 1960 the first laser, that is abbreviation for light amplification by stimulated emission of radiation. The photograph on the far right shows his invention. Arthur Shavlov, also involved in various aspects of lasers while working with Charles Townes. He received the Nobel Prize in Physics in 1964 for his contribution to laser spectroscopy. Masers and lasers discussed above produce coherent monochromatic beam of photons in a continuous fashion. This could be converted to pulse laser by using a blanker. Since then, the laser science progressed massively, and further dive into this topic is not in the scope of this lecture. The foundation for short and ultra-short pulse lasers, these having pulses duration below picosecond range, were set by Donna Strickland and Gerard Marot in the publication from 1985. They presented work on the shear-pulsed amplification laser while working for University of Rochester in the US. Their system produced infrared 10-6 nm wavelength pulses with a width of 2 picoseconds and pulses energies at the millijoule range. These scientists received the Nobel Prize in Physics in 2018 for their work on the ultra-short pulse lasers. There are a number of benefits of using ultra-short pulse lasers. Let me call these lasers as USPLs. This schematic compares long pulse lasers or LPLs with the USPLs. The pulse duration of LPL is long enough, thus a lot of thermal energy is transferring to the surroundings of laser-ablated material. This causes large melt zone and heat affected zone, also recrystallization and material recasting. Large thermal gradients causes formation and propagation of microcracks, often accelerated by laser shock waves. On the contrary, USPL pulse duration is much shorter than the carrier excitation, that is absorption of photon and impact ionization, and thermalization, that is carrier-carrier scattering and carrier-photon scattering. Thus, the thermal and structural effects are massively suppressed to a nanometer size region. This description is a large simplification, since the physics of photon interaction with metals, dielectrics, and insulators is different. As we can see, the laser ablation process is athermal, thus we are not conserving microstructural damage. Please see the micrographs above. Now, these features of USPL allow application of these lasers for fast and precise micromachining. The precise micromachining using USPL titanium sapphire laser was explored by Gerard Marot and co-workers in the subsequent years. In 1997, he published a paper presenting the first laser setup designed for micromachining with a 13 micron narrow focus deep red laser producing 60 femtosecond pulses. The micrographs on the bottom left show surface cuts produced by his laser setup. Since they were able to precisely control the laser and remove material, the next step was to assess the potential damage that the USPL laser could cause to the microstructure of ablated material. What are the envelopes of laser parameters that removes material with minimum or negligible damage of the lattice? The first paper in this subject matter was published in 2004 by Marot and Teresa Pollock. Indeed, it is possible to remove material without damaging the lattice of a crystal with the removal rates a few orders of magnitude larger than a FIB. These and other findings led to development of a laser platform capable of removing large sub-millimeter size areas precise and fast. The setup was integrated with FEI Strata dual beam at the University of California, Santa Barbara, and the research group led by Teresa Pollock. The paper that describes the new tri-beam system that could collect serial sections with a laser was published in 2012. Today, the following systems with free beams are commercially available from various electron microscopy technology providers. Now let me dwell briefly on the developments related to EBSD and TKD methods. As I mentioned before, the EBSP in SEM was born in 1973 when Venables and Harland used their custom-built rig with the StereoScan MK1 SEM. It is worth to mention some early work of Alam and co-workers in 1954 on recording high-angle Kikuchi patterns on a cylindrical photographic film. Also work of Coates in 1967 describes of Kikuchi-like reflection patterns obtained with SEM from a series of sample tilts, here ±10 degrees tilt from 111 direction in germanium sample. A composite image is at the bottom left. The onset of modern EBSD methods is dated back to mid-1980s and associated the research work of David Dingley and co-workers. First EBSP were recorded on a photofilm and later on a TV camera in 1987. At the time, the crystal orientation from the Kikuchi pattern were solved manually. The first automation of the pattern indexing was presented in 1989 by Schmidt and Olesen. They presented it within Channel software, later distributed by HKL company in Denmark. Finally, the indexation method adopted and used by Oxford Instruments from the United Kingdom. Another automation of the pattern indexing was proposed by Wright and co-workers in 1991, scientists associated with EDAX company in the USA. Image processing procedures for analysis of electron backscattering patterns based on half transformation were proposed by Krieger-Lassen and co-authors. A year later, in 1993, the full automation of EBSP processing hardware and software was published by Dingley and co-authors. That was the first OIM setup distributed by EDAX. The first CCD-based detector was used in 1993, and it was the foundation for almost 25 years for all the commercial EBSD cameras. In 2017, the first CMOS-based EBSD camera appeared on the market. It was still an indirect electron detection optical system with phosphor screen, but much faster, reaching pattern collection speed of about 2000 frames per second. The transmission Kikuchi diffraction, or transmitted EBSD method, was born in 2012 in a paper published in Journal of Microscopy. Nevertheless, the authors presented it earlier at M&M conference in 2011. Keller and Gase used the standard EBSD hardware but with a custom-designed TM sample holder for the thin film specimens. Their setup is presented on the left. Thin film samples allow significantly reducing the electron-matter interaction volume, thus mapping nano-sized domains. The next important milestone is development of detectors for direct detection of electrons. The first paper that describes application of such a detector for EBSD was published by Angus Wilkinson and co-authors in 2013. They showed that the direct electron detection gives much richer information on the Kikuchi bands, but at the expense of indexing speed to a few dozen of frames per second. One of the speed-reducing problems was that only the high-energy diffracted electrons having 80% energy of the incident beam, were recorded with this detector. Energy filtering direct electron detection for EBSD TKD allowed recording also low-energy electrons events, therefore much more Kikuchi diffraction signals are collected. Such a detector was presented in 2020 in publications of BEMS and Bielhorn. Direct electron energy detectors are compact since there is no need for bulky optical path. This led to development of a new geometries for EBSD called tilt-free EBSD. It was published by Marshall and co-authors in 2021. The detector sits flat right under the SEM pole piece, and the primary electron beam travels through a hole in the center of the EBSD detector. In such a configuration, the interaction volume of electrons with matter is symmetric, unlike largely elongated for the classical EBSD geometry with 70 degrees sample tilts. Also, the sample size is not restricted by the hardware, thus a very large flat samples are now possible to examine. Here I am listing the most important papers in various aspects of EBSD and related techniques. From key development papers to other microanalytical approaches, new indexing methods, high-precision EBSD. Next, 3D EBSD. Integration of EBSD and EDS. In situ EBSD. Transmission Kikuchi diffraction. Texture analysis. Electron channeling contrast imaging, or ECI. Certainly, this list does not exhaust the subject matter. This graph shows number of papers related to EBSD and TKD published each year according to Scopus search engine, with a total number of papers about 5,400. The key EBSD publications are also indicated. We can clearly see that the number of publications increased when the automated EBSD systems were available, first these based on CCD cameras and later CMOS chips. We can see rather a steady increase in the number of publications presented each year for almost 20 years since the CCD camera emerged. It seems that TKD methods available from 2012 is associated with visible jump in number of publications since that year. From 2017, the number of publications rapidly increased. This coincided with the CMOS-based EBSD appearance on the market. This graph shows number of papers related to EBSD, TKD, FIB-SEM and plasma FIB-SEM system published each year according to Scopus, with the total number of papers just below 500. This gives about 8% of the total number of papers related to EBSD TKD that were associated with dual beams. The first paper were published in about 2000, and for the next 18 years there was a slow increase in the number of papers published yearly. Around 2016-2018, we can see clear drop in the number of papers for FIB-SEM. That is likely rather not connected with the paper published for the plasma FIB-SEM and EBSD, this since 2016. Now to wrap up this chapter, I'm presenting some striking 3D EBSD and TKD results for specimens prepared using plasma FIB-SEM and with femtosecond laser systems. Top left image compares typical FIB and plasma FIB prepared 3D EBSD chunk of material. There is also presented massive almost 300 micron wide chunk prepared with a plasma FIB. The one of the biggest 3D EBSD volumes collected with plasma FIB is presented bottom left. Since the sample was resected from a shot-peen aluminum alloy, the top volume is not indexed. In this area there are heavily deformed nanocrystalline grains. To aid indexation of such a microstructure, the dictionary-based method of pattern indexing was used, as shown at the bottom. Top center shows large 3D EBSD of additively manufactured nickel superalloy. Such a large volume gives a lot of crystallographic information that are representative of a bulk volume. The data is impossible to obtain in a timely manner by other 3D data collection techniques. The example top right shows TKD map of a large electron transparent Ti-64 lamella prepared with a femtosecond laser. Now we are about to finish our journey and look at the current and future directions in the subject area. Let me point here that by no means this list exhausts the subject matter. We observe further improvements in direct electron energy detection for EBSD and TKD, and also energy filtering for direct electron detection, increasing the speed of pattern collection, fast, more sensitive hardware, use of spare pixel in the detectors. I-cord and E-cord method is getting more robust. More emphasis on smart spare sampling. Use of machine learning and artificial intelligence in electron microscopy. For example, live image processing, microscope auto-alignments, etc. Full microscopes integration with detectors, for example, chemisem, and techniques, for example, ECI on SIOS and Helios. Use of Python API to access functionalities of microscopes. User-friendly workflows and automations. Correlative microscopy with more imaging modalities, for example, adding XPS, LIBS, EPMA, APT, Raman, etc., and tuned workflows. Electron microscopy and correlative microscopy with full integrated inner gas workflows, Glovebox, microCT, dual beams, and TM. Increased demand of cryo-electron microscopy in material science. This list concludes my lecture. Thank you for your time and attention. I wish you have a great day. Cheers!